similar way as what we did with the Rolle's theorem. The function in this problem is e to the power x. The interval is 0, natural log 6. And if it satisfies the mean value theorem assumption, the conclusion of the mean value theorem is there is a point C that gives the slope the same as the slope of the secant line. In the graphical way, we have point A here, we have point B here. If the function value are different at two endpoints here, and we draw the tangent line, the slope of this secant line is the same as slope of the point on the curve here, somewhere between A and B. Let's see. That share the same slope, or maybe two different cases here. So I just like give the example as the graphical form to explain the mean value theorem. So that means the point, that should be the point C, that the f prime at C, or the slope of the tangent line, equals the slope of the secant line that passing the point A and point B. And the slope is calculated by fb minus fa divided by b minus a, which is just the normal slope formula, or the y2 minus y1 divided by x2 minus x1. So for the assumption of the mean value theorem, number one, the function is continuous on the closed interval 0, natural log 6. Our function is e to the power x. That's the exponential, the increasing exponential, which is continuous by the nature of it. Or we can say there is no restriction or no number that make it undefined. So then this function is continuous on the closed interval 0, natural log 6. So we can say this is continuous everywhere. Okay. Number two, the derivative of the exponential, which is the same form, or e to the power x. So we can say f prime of x is differentiable on the open interval 0, natural log 6. Only two assumptions for the mean value theorem, because we don't have to follow the restriction that the function value at point A must be the same as the function value at point B, because that is the assumption for the Rolle's theorem. Okay, if think about the mean value theorem, if the FA equals FB, it's just change from the mean value theorem back into the Rolle's theorem. And another way I would say the Rolle's theorem is the special case of the mean value theorem. So by the conclusion of the mean value theorem, there exists, or there is at least one value C such that C on the open interval 0, natural log 6, such that the f prime at C equals fb minus fa divided by b minus a, or the slope of the tangent equals the slope of the secant line passing the two endpoints. And from the derivative, we can use the derivative form that we obtained from the assumption number 2. But the function value, let's put on the side here, the function value at the two endpoints. So the f at A, point A is 0 and point B is natural log 6. I just put it on the side just to make the problem cleaner. I mean the area, working area cleaner. The FA is 0. F at 0 is e to the power 0, or just 1. F at point B, or f at natural log 6, is e to the natural log 6. What do we have as e to the natural log 6? The cancellation law, right? Which is 6. Now we have the two function values put it back into the the working area. Replace x with the c on the left expression, which is e to the power c, equals the function at b, which is 6, the function at a, which is 1, divided by b minus a, or natural log 6 quantity minus 0. You don't have to put parentheses around if you know exactly like log 6 by itself and then subtract it by the value. I put the parentheses just in case that the number for the a is not 0. I don't want you to get confused with, oh, can I subtract 6 and the value a that you put in? And actually, the answer is no. All right, simplify the right hand side. We have 5 divided by natural log 6. And then to get the value c, which is our goal to find out what is this value c on the open interval. So we just treat the 5 over log 6 as one real number. To get c down from the power of the e, you take natural log both sides. So natural log e to the power c equals natural log of the quantity 5 over natural log 6. And do not cross log and log, okay? That's where you misuse the rule. Leave it the way it is. And then log and e cancel out. You get c equals natural log of the quantity 5 over natural log 6. What do you have to do next? You just put in a calculator and get the approximate value. And as you see this, the form that you see natural log 5 over log 6, this form is called the exact form. Exact form. When you put in a calculator, you get a number. I believe it's about 1.03. Okay, you can help me verify that number if you have a chance. So it's about 1.026 something. So if you keep it two decimal places, so it's about 1.03. And then check again, is 1.03 on the interval 0 natural log 6? Yes, it is. As if you want to verify more, what is the value of natural log 6? It's 1.79. So natural log 6 here is about 1.79. So 1.03 is less than 1.79. So we keep this number. We keep this number. And in the graphical way to explain this, the exponential graph at the point 0, the value is 1. At the point natural log 6, the value is 6. So the graph going up like this. Okay, just this portion of the graph, not the straight line. Let me clean this up a little bit, make it looks like a curve. Okay, look like a curve from 0 to log 6, and the log 6 is about 1.79. The slope passing through these two endpoints has some slope like as the value 5 over log 6, and then there will be some point on the curve that share the same slope, which the point that we found is 1.73 that has the same slope. So that one is the f prime at c, and the dotted line has the slope m equals 5 over natural log 6, which is the slope of the secant line.